Electrical conductivities of solids are spread over the widest range of any physical property, extending over 27 orders of magnitude, ranging from 10 to the power minus 20 to 10 to the power 7 ohm inverse meter inverse. On the basis of their electrical conductivity values, solids can be classified into three categories: conductors, insulators, and semiconductors. Conductors have extremely high conductivity values, ranging from 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. Insulators have extremely low conductivities, ranging between 10 to the power minus 20 and 10 to the power minus 10 ohm inverse meter inverse. Semiconductors have conductivities in the intermediate range, from 10 to the power minus 6 to 10 to the power 4 ohm inverse meter inverse. Let's first study conductors in detail. Depending upon the mode of conduction, conductors can be classified into two types: metallic conductors and electrolytic conductors. In metallic conductors, the conduction is due to the movement of electrons. They are also referred to as electronic conductors. Metals belong to this category and conduct electricity without undergoing any change. On the other hand, in electrolytic conductors, the flow of electricity is due to the presence of ions. This type of conductors conduct electricity only in their molten and aqueous states. In solid state, they conduct electricity to a very small extent, and that too due to the presence of imperfections in them. Electrolytes like sodium chloride and potassium chloride are electrolytic conductors. The conductivity of metals depends upon the number of electrons present in the valence shell of their atomic orbitals. The electrons of a single isolated atom occupy atomic orbitals that form a discrete set of energy levels. When the atoms come close together, the overlap between their atomic orbitals results in the formation of molecular orbitals. When a large number of atoms come together to form a solid, the number of molecular orbitals becomes exceedingly large. Consequently, the difference in the energy between them becomes very small. Thus, in solids, the energy levels form continuous bands of energy rather than discrete levels of energy. This leads to a band of molecular orbitals of almost a continuum of energy. The band that holds the valence electrons is called the valence band. The other band, which is slightly higher in energy and is formed by the overlap of atomic orbitals, is called the conduction band. In metals, the valence band overlaps the conduction band. This results in easy flow of electrons under an applied electric field, and the metal shows conductivity. In insulators, as you can see, the electrons in the valence band are separated by a large gap from the conduction band. The gap region is called the forbidden zone. This gap is so large that enough energy is not available under normal conditions to promote electrons from the valence band to the conduction band. Hence, the solid behaves as an insulator. In semiconductors, the energy gap between the valence band and the conduction band is smaller than in insulators. The thermal energy available under ordinary conditions is sufficient to excite some electrons from the valence band to the conduction band. Thus, only a small amount of current can flow through them. Thermal energy is one of the main mechanisms for electrons to be excited to the conduction band. Therefore, the conductivity of semiconductors depends strongly on the temperature of the material. At absolute zero, semiconductors are perfect insulators. But at room temperature, there is enough thermal energy to allow the occasional electron to jump. And this gives the semiconductor limited conductivity. Semiconductors can be classified into two broad categories. First, there are intrinsic semiconductors. These are composed of only one kind of material. Silicon and germanium are two examples of intrinsic semiconductors. They are also called undoped semiconductors. The other type of semiconductor is the extrinsic semiconductor. These are made of intrinsic semiconductors to which other substances have been added to alter their properties. With a small energy gap in the semiconductors, the presence of a small percentage of a doping material can increase the conductivity dramatically. You are already aware that the electrical conductivity of semiconductors is very low. The addition of a small percentage of foreign atoms to a regular crystal lattice of an intrinsic semiconductor, like silicon or germanium, produces dramatic changes in its electrical properties. Such impurities introduce electronic defects in the semiconductor and produce an N-type or P-type semiconductor. Let us first look at N-type semiconductors. In an N-type semiconductor, the doping atom usually has one more valence electron than the host. The addition of a pentavalent impurity such as antimony, arsenic, or phosphorus contributes free electrons to the silicon or germanium lattice. This produces an N-type semiconductor. The free electrons contributed by the pentavalent impurity are responsible for conduction of electricity in an N-type semiconductor. Let us now study P-type semiconductors. The addition of a trivalent impurity, such as boron, aluminium, or gallium, to an intrinsic semiconductor creates deficiencies of valence electrons. As you can see here, one electron is missing from one of the four covalent bonds in the silicon crystal lattice. These are called holes. The dopant atom can accept an electron from the covalent bond of the neighboring atom to complete the fourth bond. This causes the neighboring atom to lose a bond electron and results in the formation of a hole at the neighboring site. This shift in electrons from the neighboring site to the hole continues. It is important to note that holes are the majority carriers, while electrons are the minority carriers in P-type semiconductors. Also, the direction of conduction of electricity is opposite to the movement of holes in p-type semiconductors. Let us now take a quick look at the applications of p and n-type semiconductors. The most important application is in a p-n junction diode. Here, a p-type and an n-type semiconductor are brought together in close contact, creating a depletion region. In the depletion region, p-type holes recombine with n-type free electrons, allowing current to pass. In a light-emitting diode, LED, this current produces light. A photodiode converts light into electricity. The common, traditional solar cell used to generate solar power is actually a large area photodiode. It is important to note that in a diode, current can flow in one direction only, but not in the other, and this forms the basis of digital electronics. One of the most popular applications of the diode is in rectifiers. Rectification is the conversion of alternating current into direct current. A rectifier is a device that allows electrons to flow only in one direction. Another application of N and P semiconductors is in the transistor. It is a semiconductor device used to amplify current. There are two types of standard transistors, NPN and PNP. The letters refer to the layers of semiconductor material used to make the transistor. A large variety of compound semiconductors, composed of elements from two different groups of the periodic table, such as 13, 15 and 12, 16, are widely used in communication devices. These semiconductors simulate an average valence of 4 electrons, as in germanium and silicon. Some typical compounds of groups 13, 15, like indium antimonide, aluminium phosphide, and gallium arsenide, have revolutionized the design of semiconductor devices. Gallium arsenide has some electronic properties that are superior to those of silicon, which makes it an excellent material for space electronics. Group 12-16 semiconductors are materials whose cations are from group 12 and anions are from group 16 in the periodic table. Zinc sulfide, cadmium sulfide, cadmium selenide, and mercuric tellurite are examples of groups 12-16 compounds that find applications ranging from biomedicine to solar cell technology. Transition metal oxides are another category of substances that show diverse electrical properties, ranging from strongly metallic to insulating. Oxides like titanium 2 oxide, chromium 4 oxide, and rhenium 6 oxide behave like metals. Rhenium 6 oxide can be compared to metallic copper in conductivity and appearance. Oxides like titanium 4 oxide, vanadium 6 oxide, and many metal 2 oxides behave as insulators. For certain metal oxides like titanium 3 oxide, vanadium 3 oxide, and vanadium 4 oxide, there is a transition in electrical property from metallic to insulators at a certain temperature.